Hi and hello there, welcome to the new video of the course, and in this particular video we are going to understand a difference between analog and digital signal, and based on that particular signal we can easily understand difference between analog and digital electronics, like how exactly digital electronics get a slight advantage over analog electronics when it comes to storage, right? So without wasting any further time, we'll straight away jump to our session. Alright, so I had drawn two waveforms. Okay, so in the very first waveform, or in the very first diagram, what you can see is that this particular waveform, it is oscillating between 2 points or 2 junctions. That is, it is attaining maximum voltage, right, and then it is becoming zero, and at the end it is attaining minimum voltage, right? But over here the case is slightly different, right? Over here it is starting from zero, moving up till certain point, okay, exceeding and again going back to zero, and after that it is decaying, right, and again it is coming back, moving above zeroth line, okay, something like this. Okay, then if I ask you what would be the name of this particular waveform, you would say, like, we cannot give any name to this particular waveform. Okay, but if I ask you that what would be the name of this particular waveform, right, so you can easily tell that the name of this particular waveform, it is what? It is sinusoidal, right? So basically it is sinusoidal waveform. Just a second. Yeah, it is sinusoidal. It is sinusoidal waveform. Whereas if I ask you what would be the name of this particular signal, so now you would get confused. Before moving to this particular point, if I ask you, can a sinusoidal waveform be an analog signal? Okay, or basically can analog signal be a sinusoidal waveform? You'll say yes. So basically this particular sinusoidal signal can be an analog signal as well. Okay, but can this particular waveform be a sinusoidal or a cosine waveform? You would say no. So basically it is pure analog waveform. Analog signal or analog waveform, right? Because as such it does not have any traditional curve. As you can see, this is a traditional curve for sinusoidal waveform or analog signal, right? So a sinusoidal signal can be an analog signal, but an analog signal can never be a traditional waveform, right? I mean this particular signal. Okay, so you can also take an example of cosine waveform. So again, cosine waveform, it is a part of analog signal, right? I hope you got this particular point. And the important thing what we can see over here is this. Just a second, let me decrease the thickness of my pen. Alright, let's suppose at t is equals to 0.1 second, the voltage of this particular waveform, it is 0.1 volts. Now let's suppose if I'm moving to t is equals to 0.2 seconds, so at t is equals to 0.2 seconds, the voltage is 0.2 volts. On the similar note, if I am seeing this particular waveform, so it is, let's suppose that t is equals to 0.1 second, right? T is equals to 0.1 second. The voltage of this particular waveform, maybe it is 0.1 volts only. At t is equals to 0.2 seconds, right? Maybe it is 0.2 volts, right? At t is equals to 0.3 seconds, as you can see, it is decaying, right? It is decaying, something like this. But if you could see very clearly, let's suppose it is, just a second, let's suppose it is minus of 3 volts, example I'm taking. But if you could see very clearly, over here this particular waveform, it is continuous in nature, right? And over here as well, this particular waveform, it is continuous in nature. Okay, it is continuous in nature. As you can see, it is continuous in nature. So what we can conclude over here is that, let me just increase the thickness of my pen. Alright, so the very first point that we can conclude over here is that let me write over here, in analog electronics, we deal with continuous waveform or continuous signal, continuous waveform or signal, right? Continuous waveform or continuous signal. Okay, that is magnitude changes with respect to time. Magnitude of this particular signal, it changes with respect to time, or even you can say amplitude. Okay, so that is magnitude of the signal changes with respect to time, right? What I meant to say is, over here at t is equals to 0.1 second, it was 0.1 volt. At t is equals to 0.2 second, it was having 0.2 volts. At t is equals to 0.3 second, maybe this particular waveform would achieve 0.3 volts, right? So that means what? For every second, the value of this particular curve, or the value of this particular signal, it is changing. Okay, I hope you understood this particular thing. And as I told you examples in the previous sessions, example of the analog electronics or the circuits are amplifier, rectifiers, etc. So I'm not writing over here. And the second point is that the analog electronics is used for processing the analog signals, right? Analog electronics or circuit is used for processing analog signals. Okay, now we'll come to the disadvantage of this particular analog circuit, right? So let me move to the disadvantage. Let me just increase its thickness. Great. So now the major disadvantage of this particular analog signal is that, see, let me write this particular sentence. Just a second. As I told you in the previous session only, it cannot store. Okay, it cannot be used as a storage element or storing element, right? So let me write over here. Now, since the magnitude of this signal is changing with respect to time, right? The magnitude of the analog signal is changing with respect to time, right? Is changing with respect to time. Therefore, we cannot store such signal. Therefore, we cannot store such signal or analog signal, right? Such signal. Okay, now we'll try to understand this particular thing with the help of one example. Okay, so for that, what I will do, let me just take one voltage source. Okay, I'm drawing this particular diagram roughly so that you should be in this situation to understand this particular concept in depth. Okay, let's suppose this is your voltage, extremely sorry, let me draw a sinusoidal voltage source. Let's suppose if I am drawing this particular sinusoidal voltage source, right? I mean, I'm providing an AC signal, right? AC signal. Okay, I'm providing this particular AC signal to, let's suppose, capacitor. I'm providing this particular AC signal to a capacitor. So let's suppose this is your, we'll take certain different color, maybe this one, yeah. So let's suppose this is your capacitor, something like this. Okay, just a second. So what I am doing, I'm providing this particular, just a second, yeah, I'm providing this particular AC signal to this particular capacitor. Okay, this is your capacitor. Okay, so before coming to that particular point, let me just draw a graph roughly. Let me just draw one graph roughly. Okay, so let's suppose this is that particular graph, right? Let's suppose if I'm taking only one waveform, maybe something like this. As we all know that this particular waveform, it will look something like this, right? Okay, I'm not drawing the inverted form of this particular waveform because it is not at all required as of now. Okay, I'm drawing its projection over here. Okay, something like this, right? So as you can see, this particular part, okay, it is equal to this one, right? So what I had done, I had divided this particular part from the middle. Okay, so let's suppose this particular waveform, it is moving from 0 to maybe 5 volts. Okay, so this is your plus 5 volts, great, and this is again 0 volts. Okay, great. So Look at this particular half very clearly. As you can see, as this particular waveform, it is advancing, right? It is advancing, so your capacitor is charging, right? So what I will do, I will just move this particular waveform over here. Okay, I'll move this particular waveform over here, and extremely sorry, I just forgot to write the plot. So this is your voltage versus time graph, right? Okay, so what we can see over here is that from 0 to 5 volts, waveform is advancing, and thus capacitor is charging. Capacitor is charging, right? Capacitor is charging. Great. But now at the very next moment, see over here, as soon as this particular waveform reaches at this particular point, so this is your 5 volts, right? This is your plus 5 volts. As soon as this particular waveform reaches at 5 volts, so you can clearly see that your waveform starts to decrease, right? In this way, it is decreasing in this way, right? I hope you are getting my point. So from 5 to 0 volts, from 5 to, just a second, yeah, from 5 volts to 0 volts, what exactly is happening? So as you can see over here, at this particular point, exactly at 5 volts, the capacitor was charged, right? 5 volts. But as soon as this particular waveform is, decreasing in nature, right? From 5 volts it is moving to 0 volts, so the capacitor will discharge. Okay, I hope you are getting my point. Capacitor discharges. Great. So that means what? Over here, in case of sinusoidal waveform, capacitor is not able to hold the charge, right? So this is the important conclusion. So the conclusion is that in case of sinusoidal signal, okay, so this is just a sinusoidal signal, but since we are dealing with analog signal, so what we can write, in case of analog signal, in case of analog signal, right, a capacitor is unable, or it fails to hold the charge, right? To hold or to store a charge, okay. And by charge, what I mean is electrons. To store electrons. Charge means what? Electrons. Okay, I hope you understood this particular part very well. Okay, great. And there is another drawback, but before that, let me add one more slide over here, because it seems that I may require one more page. Okay, yeah. So the fourth point is high noise is produced during processing of analog electronics. So let me write over here, fourth point, just a second. High noise is produced during the processing of analog signal, during the processing of analog signal. I'll write over here only signal. Okay, by this what I mean is, let's suppose we all know that analog signal, the example of analog signal is audio signal, right? So I will write over here example. Let's suppose if I'm taking example of analog signal is audio signal. Example of analog signal is an audio signal, or your heart signal, right? ECG signal is an audio signal, right? Audio signal. Okay, so let's suppose if I'm singing, okay, I'm not a good singer, but let's suppose if I'm singing, right? So let's suppose I'm person A, I am singing, so I have some X frequency, right? I have some X frequency of my sound wave, right? Frequency. So my sound wave might have X frequency. Let's suppose I have one mischievous friend who is banging the bench, okay, or banging the drum, whatever it may be. He's banging something, maybe a bench or maybe a drum. So that have some Y frequency, right? Y frequency, Y frequency. And I have some another mischievous guy who is banging some, maybe who is banging Stephen, right? We are in school or we are in college, right? So the name of that guy is C, and he's banging his Stephen Z, okay. And let's suppose that a Tiffin is producing some Z frequency of waveform, right? So now obviously our audio signal is mixture of all these three waveform, right? So our audio signal is mixture of all these three frequencies, okay. Or you can also take example as if I'm singer, so obviously my the other guy who is banging a drum, the other guy who is banging a guitar, it's up to you. But okay, for to explain this particular concept in little comedy way, I had just taken this just a random example, right? So let's suppose uh, A, which is me, who is a singer, okay, and you all know that I'm not a good singer, but still I'm able to produce a sound wave which is of X frequency. There is one of my mischievous friend who is banging the bench, okay, and that bench is responsible to produce the sound wave of Y frequency. And there's another mischievous guy who is banging his tiffin, and that particular tiffin is producing a sound wave of Z frequency. And obviously our audio signal is mixture of all these frequencies, right? Is mixture of all these frequencies, all these frequencies, right? Frequencies, and these frequencies add up, right? And this particular frequencies add up, and thus it creates noise. What I meant to say is, see, let's suppose we'll take this color. So let's suppose X frequency is something like this, Y frequency is something like this, and Z frequency it is something like this. So when we add up, we are getting something like this kind of signal, right? And when we are feeding this particular signal, or this particular, what I can say, obviously this signal has frequency, right? So this particular signal and the what I can say, a processing unit. So what exactly it does, it processes the signal, okay, but still it has some noise, right? Okay, let's suppose if we want this particular signal, okay, desired signal, okay, desired signal, but still with that particular signal, this particular thing, as you can see over here, this is noise. It gets add up, even though we are processing it, but still this particular analog processor, they are not so good processor, right? So as you can see over here, like this is my voice, right? Maybe this is drum's voice, and maybe this is the Tiffin's voice, right? I mean the Tiffin's signal, right? And with this there would be some surrounding noise. Maybe we are carrying our what I can say, orchestra, or carrying our music in some traffic areas, right? So this is that particular vehicle's noise, maybe, okay. This can be the noise of this particular vehicle, okay. But when we are feeding this particular signal to the processor, this processor will try to eliminate this particular noise, but again it will not at all eliminate it completely, right? There might be certain noise present in that particular signal. So that's the main reason that in case of analog circuits, or in case of analog electronics, the signal which you are getting, it has high noise, right? It has high noise. I hope you are able to understand this particular example. Let me erase this particular thing, okay. So whenever you will refer my PDF, you would be in this situation to understand this particular concept, right? So what I told to you, this particular frequencies add up and make a desired signal, right? But with that particular desired signal, there might be some noise added with this particular signal, right? So when we when we feed this particular signal in processor, we get desired signal, that is this particular three signals plus a noise signal. As I told you, noise can be anything. Maybe noise is generated because of some vehicles which is moving nearby to us, and we are we are that guy who are singing, or who are holding our orchestra in some traffic areas and all, okay. As I told you, we all three of us are mischievous guy, right? So maybe in our audio signal the noise is also getting added, right? So the analog processor are not that much advanced, right? It cannot eliminate the noise completely. So that's why high noise is produced, okay, or we are getting high noise even though by processing the analog signal. So I hope you understood this particular part. Great. Now moving further, this is the last point, that is fifth point, and this is the and the point is that analog circuit are tough to design. Analog circuit are tough to design. Are tough to design. Tough to design. Great. So this is the fifth point, okay, and this particular point you would be in this situation to understand when we will design certain analog electronics or analog circuit. Although we had design, I hope you all know, those students who had enrolled in my previous courses, you all know that what you all know is that we had studied certain mini projects, right? And in that particular mini projects we had designed analog circuits, and at that time you understood that it is taking hefty amount of time to design analog circuits. Although we are getting good proper, I mean proper output, but still it is consuming hell amount of time and hell amount of efforts, right? But scenario would be different when it comes to digital electronics, right? Just need to have a certain logic in your mind and that's it. You can easily implement it with the help of digital electronics, and that's why it is said that analog circuits are tough to design, right? So I hope you understood this particular thing, right? Now moving further to digital electronics. All right, so this is how the waveform looks in case of digital electronics, right? So just a second, let me take this particular thing, let me decrease the thickness of the pen, right? So now you can clearly see that digital electronics, it is not continuous in nature. It is not continuous in nature. It is not. Just a second. The first point is that the waveform is not continuous in nature. Now you will say, but sir, we can clearly say that this particular part, it is getting repeated, it is repeated once again, so how you can say that it is not continuous? See, try to understand in this way. See, at t is equal to at t is equals to 0.1 second, let's suppose I'm talking at this particular point, at t is equals to 0.1 second, your voltage is what? Let's suppose it is 5 volts, right? It is 5 volts. Now let's suppose at t is equals to 0.2 second, right? So at t is equals to 0.2 second, we have still the same amplitude, that is 5 volts. So as you can see, in case of analog electronics, at every second the voltage was changing. For 0.1 second we were getting 0.1 amplitude, right? For 0.2 second we were getting 0.2 voltage. But in case of digital electronics, we are getting constant amplitude. Okay, we are getting what? We are getting constant amplitude even though the time is changing rapidly. I hope you are getting my point. So that is why I told it is not a continuous signal, that it is attaining certain stable value, then it is decreasing. Okay, then it is quickly becoming zero. It is attaining a lower value, again it is attaining a higher value, right? So it is fluctuating between these two values only. Okay, whereas in case of analog electronics we were getting the middle values as well. Maybe if the waveform is moving from 0 to 5 volts, right? So we were able to achieve 2 volts, 3 volts, 1 volts in between, right? But over here we are unable to do so. Okay, great. So moving to the further point, let me see what was the next point which we discussed in analog electronics. Yeah, as I told to you, in digital we deal with non-continuous waveform. Okay, great. And now moving further, now we'll see how exactly we are able to store certain things when it comes to digital electronics, right? So let me increase the thickness of the pen. So the second point is, just a second. So the second point was digital electronics, or the circuit is used for digital signal. Okay, for processing a digital signal. Just a second, I will write that particular point. So digital signal, sorry, digital circuit or digital electronic or circuit is used for processing digital signal. Okay, that we'll see in the upcoming video, so need not to worry about this particular part. That's not that much important as far as the introduction part is concerned, right? So the third point is pretty important. Third point is what? It can be used as a storage element, right? So see, what we can write is, now since, just a second, now since the signal is able to achieve a stable value, right? A stable value for certain time period, for certain time period, therefore it can, just a second, I will see how exactly I had framed the sentence in case of analog, and I'll therefore it can store such signal. Now you would be understanding that how exactly we store the information, right? So for that, what I will take, just a second, let me take this particular color and see over here, this particular thing, it is representing that I'm see, this particular thing, it is representing that I'm providing a digital signal. On contrary, if you are able to see such kind of signal, it represents that I'm providing an analog, a sine wave signal, right? So, and this represents that I'm feeding square wave signal, or in short, a digital signal to a circuit. So let me erase this particular part. Okay, let me erase this particular thing, and let me just complete it like this. Okay, so rather than representing in this way, what I will do, see, we all know that square wave moves in this way, right? Positive, negative, positive, negative. Okay, so only think about this particular part. Just a second, I will take different color. So now just think about this particular part. See this one, this particular part. Okay, this particular, only positive half. Just think about the positive half. Oh, just a second. Yeah, just think about this positive half. Okay, and now see, since we are dealing with plus 5 volts, so let's suppose it is plus 5 volts. Okay, so what, rather than representing this particular voltage source in this way, what I can do, I can also represent it in this way, plus minus. Okay, I can also represent it in this way, indicating that we are dealing with this particular part, right? Okay, and then I'm feeding this particular thing to the capacitor, something like this. Let's suppose this is your capacitor C, right? And now I am drawing that particular waveform once again. So this is your waveform, something like this, right? Now it is moving from plus 5 to 0 volts, so it can be represented in this way, so plus 5 to 0, something like this, right? And now what I'm doing, I am dividing this particular waveform from the middle, right? So it would be something like this. Okay, it would be something like this. Great. All right, so now what you can see over here, from, just a second, just for your understanding purpose, what I can write over here, let's suppose this is 0 volt, let's suppose it is 5 volts, and then again it is going to 0 volts. Okay, so over here what you can see, let's I'll just write over here, this is plus minus 5 volts, right? From 0 to 5 volts, just a second, from 0 volts to 5 volts, capacitor is charged. Capacitor has charged, right? Over here same thing was happening, but over here what was happening is that capacitor is charging, so it is charging, it has not charged. Why? Because see, uh, at 0 volts, sorry, at 0 time t is equals to 0 second, obviously the charge on capacitor would be 0. At time t is equals to 0.1 second, since it is giving 0.1 volts, right? So capacitor charge on the capacitor would be 0.1 volts, right? Similarly, at at time t is equals to 2 seconds, so the voltage, it will provide 2 volts, so the capacitor will also charge up to 2 volts, right? So when this particular voltage source, it will give 5 volts to the capacitor, so obviously the charge on the capacitor, or the what I can say, capacitance would be 5 volts, right? I hope you are getting this particular point. Great. But over here, from starting only, we are providing 5 volts, as you can see in case of analog signal, what was happening is, we were starting from 0 and we were moving to this particular part, right? So capacitor was charging, it was not charged. Remember this particular point very, very clearly. It is charging, okay? It was not at all charged, right? Let me take different color to represent this particular sine wave, so that there shouldn't be any confusion in your mind, right? So this was your analog signal, it was moving in this way, right? Something like this. So as you can see, the capacitor will charge, and in this particular scenario, in case of this particular what I can say, a square wave, capacitor has already charged up till this particular point, when it reached up till this particular point, right? And now from 5 volts to 0 volts, maybe up till this particular point, right? Up till this particular point I will talk. Sorry, not this one, extremely sorry. Up till this particular point, from 5 volts to 0 volts, 5 volts to 0 volts, charge will remain constant. Now capacitor is still charged. Capacitor is still charged. Capacitor has charged. It is charged only, right? Capacitor charged. And now at as soon as this particular waveform drops to 0 volts, discharging starts. Discharging starts, right? Discharging starts. Forget about this particular point. Just look at this particular point. This was your analog signal, right? It was moving in this way. It was moving in this way, right? But over here, see, at this particular time during analog signal, when we were dealing with analog signal, capacitor suddenly charged to discharge, right? But in case of digital signal, the charge is able to sustain in the capacitor, or capacitor is able to sustain that particular charge, right? So what we can say, what we can conclude over here is that in case of digital signal, or in case of digital electronics, just a second, in case of analog signal, capacitor is unable to hold charge, okay? In case of digital signal, capacitor is able to hold charge for certain instant of time, right? So I will write over here, in case of digital signal, capacitor a capacitor is able to hold a charge for certain instant of time, or I can write for a few seconds, or for few seconds, right? For few seconds, okay, or for certain time period, right? Hold a charge for certain time period, okay? Or what I can say, this charge is nothing but your electrons. Obviously we all know that electrons is nothing but your information. This is nothing but your information. So this information can be in form of images. So the amount of that's a different scenario. I'm not going to explain this particular part, like the amount of electrons that that is holding the capacitor, right? It signifies what exactly the storage is, right? So information can be in form of images, right? It can be videos, etc., etc. But I hope you understood that how exactly in case of digital electronics we are able to store the information, or we are able to hold what hold the charge, or basically how digital electronics plays a significant role as far as the storage is concerned. Again I am repeating, see, in case of analog electronics, or in case of analog signal, what was happening, capacitor was charging and discharging very quickly. But in case of digital signal, what is happening, capacitor charged as soon as we plug this particular 5 volts, right? Or as soon as we provide this particular digital signal, okay? And from 5 volts to 0 volts, again see, the capacitor or the charge on capacitor is stable, but in case of analog signal it was decreasing quickly, right? I hope you are getting my point. But as soon as this particular waveform attains 0 volts, then capacitor will start to discharge. Okay, I hope you are getting this particular point. Okay, that means what? For this particular time, okay, for this particular time the capacitor is holding charge. Right over here, just a second. For this particular time, capacitor is able to hold a charge, right? To hold electrons or charges, in short, or charge. Okay, so that means what? A digital in case of digital electronics, we are able to hold what? We are able to hold electrons, and thus what you can say is that we are able to store a charge, right? And thus we can say that digital electronics, or the significance, or the basic, or the fundamental significance of the digital electronics is nothing but it is to hold what? Store. It is hold, or it is to store electrons, or basically what? It is used as a storage element, right? I hope you understood this particular part very well. Okay, and the next point is that, see, since we are dealing with only this particular one frequency of the signal, right? So what we can say is that frequency produced, or the digital, just a second, what we can say in the next point is that, just a second, this was your third point, right? So the fourth point would be less noise is produced in processing of digital signal, right? In just a second, I will see how exactly I frame the sentence, and I will write as it is: during the processing of digital signal. Okay, during the processing of digital signal. Less noise is produced during the processing of digital signal. I hope you are understanding this particular point. Less noise is produced during the processing of digital signal. Why? Because, see, the waveform is moving in this way: positive, negative, positive, negative. So obviously it has only one frequency, f is equal, so it is only one frequency, right? It can be anything. Let's suppose I am talking about x frequency, x hertz. But in case of analog signal, so see over here, the analog signal can be in this way, right? So as you can see, it has maximum frequency at certain points, and at certain point it was having minimum frequency. So basically is a mixture of x plus y plus z, or any combination of frequencies. And when we are feeding it to the respective processor, so in case of digital, if I'm feeding it to the, I'm writing it in short form, digital processor, so it is able to attenuate noise, right? It is able to attenuate the noise, right? So noise is getting suppressed. Obviously there would be certain noise, but it would be quite less as compared to analog. Okay, and then we would be getting certain signal that is required, right? But in case of analog, what is happening, if we are feeding this particular signal to the analog processor, so it will give the signal as it is. Okay, just a second, but there would be high noise, and then we would be getting the signal which we want, right? So as you can see over here, the noise component is high, and over here the noise is less, although it is present, but it is very less, right? Noise is less. Okay, I hope you are getting this particular point. And the fifth point is, it is easy to design. It is easy to design. That means what? Digital circuit, it is easy to design. Okay, so I hope that you understood this particular concept in depth. Again, we will revise this particular concept very quickly. So yeah, this is where we started. So the analog signal is that signal which is a continuous, okay, which is continuous with respect to time. That means what? At t is equals to 0.1 second, we are getting 0.1 volts. 0.2 second, we are getting 0.2 volts, right? So as you can see, this is a sinusoidal waveform. Okay, it is also known as analog signal. And this particular signal, it is also known as analog signal, but this particular signal cannot be named as sinusoidal signal. Okay, I hope you understood the basic difference between these two waveform. and obviously the analog circuit is used for processing the analog signal. And in analog electronics we deal with this kind of signals where the signals are continuous, right? Great. And the third point, it plays a very significant role to bifurcate or to create a difference between analog and digital electronics, is that analog in analog electronics we cannot store anything, right? So since the magnitude of analog signal is changing with respect to time, therefore we cannot store such signal. So as you can see, the capacitor was charging and then it was quickly discharging in case of analog signal, but in case of digital signal, it charged and then it stayed, I mean it kept its particular charge for certain time period. That means what? It is holding electrons, which signifies that it can be used as a storing device, right? I hope you understood this particular point. Great. Now moving to the further point of analog electronics, so it was like it was providing high noise after processing, right? So as I told you myself, if I'm singing, I'm producing X frequency. Other guy who is my friend, he is providing Y frequency by banging the bench, and Z frequency it is responsible to produce from the banging of the tiffin, right? So when we add this particular frequency of signal, we will get different kind of frequency of signal plus noise, right? So analog circuits, it is not able to attenuate the noise at that particular level. But in case of digital electronics, as you can see over here, it has almost suppressed the noise, but in case of analog electronics it was not able to suppress the noise in that way, right? So that was the major drawback of the analog electronics over digital. And in case of digital, the waveform is not continuous. As you can see, at 0.1 and 0.2 seconds we are getting the same amplitude, and therefore the digital circuit is used for processing of digital signal. Obviously that we'll see in the upcoming courses. And now since that signal is able to achieve a stable value for a certain time period, therefore it can store such signal, right? So this we had seen over here. Okay, so I hope you understood this particular concept in depth. If you have any doubts, feel free to ask me at any time. Thank you.